Hello students, welcome back. So in my last class, I discussed about the wave function, and I told that in order to define a quantum state, our wave function should be square integrable. Now, square integrable means if I integrate mod of psi x square dx, this should be a finite number less than equal to, if I go minus infinite to infinite, that is if I writing, say, if I go to the all space, here is a one dimensional, so I'm going from minus infinite to infinite, then this should be finite. And this condition is requirement if a wave function, for wave function which is going to which we are going to use for defining a quantum state. Now, why do we require this condition? This condition we require because mod of psi x square is shows the probability density finding the particle at x. If you multiply this one, this becomes probability, and the sum of probability or integration of probability, whole probability should be 1, because particles should be somewhere from minus infinite to x, infinite to minus infinite to plus infinite. So this should be equal to 1, and so if it is a square interval, we can make it 1, we can normalize it. So that is the reason we need a square integrable function. And the second thing I told, if I have a psi1x and psi2x, two function, and when both are normalized, then I can construct a third function psi3x, which is the linear combination of these two functions, psi1x plus beta psi2x. And now this function is also normalizable. That means it also can be associated with a quantum state. In other words, if I say if psi1x, psi2x are the element of a vector space, in quantum mechanics we call this vector space Hilbert space, then their linear combination is also a element of a that Hilbert space. So this property is called superposition, and this property we generally don't see in classical mechanics. So this superposition property of wave function is associated. Superposition property of wave function is, or states, is associated with quantum mechanics. Then that means particle can stay at a multiple state at a time. Now, the second property I'm going to discuss the quantization effects in quantum mechanics. So in quantum mechanics, if you restrict a particle, then its angular momentum, kinetic energies, uh, and linear momentum, they generally are quantized. So let us see this with an example. So say I am taking uh, example of particle moving in a circular ring. So say particle is moving in a circular ring of radius r. So my particle of mass m is moving in this circular ring, and here I can say the length of this ring L is equal to 2 pi r. Now particle is moving continuously here, so I can say that the wave function of this particle should be periodic. That means if I say psi x is the wave function for this particle, then this condition should prevail. Psi x plus L should be equal to psi x, because particle is keep repeating its position. So it is going, say, x is equal to 0, starting from x is 0, it's going at x is equal to L, and then again going x is equal to 2L, x is equal to 3L. So these are same positions. This one, this one, this one, this one, same positions. So the wave function should satisfy this condition. This is the first thing. And now you can see a circular ring is equivalent to a infinite length because particle is continuously moving. So you can take L as a infinite. Now let us find the first wave function for this particle, and before that let me write the Schrodinger equation. So Schrodinger equation is H psi is equal to E psi. This is my Schrodinger equation, Hamiltonian. And now in order to make things little bit easier here, I assume my potential energy also zero. I'm taking Vx is also zero. So in that case, what will happen? That case, my this equation will become very simple. H cut square 2m del 2 psi upon del x square and is equal to E psi. Now here I want to show when the potential energy is zero, my E is positive. My energy is or particle is has positive sign. So let us first prove this one, and then I will find the wave function, and then we will calculate the observable momentum, kinetic energy, and angular momentum. So let us first find the uh, sign of this energy. So let us multiply this equation by psi star. So this becomes del 2 psi upon del x square E psi star x psi. So let us solve it further. So now you have integrate this equation from 0 to L because we have a the circular ring has total length L. So I am integrating this from minus h cut square 2m. I'm 0 to L psi star del 2 psi upon del x square, and then this is a E 0 to L psi star psi tx. Let us solve this one minus h cut square 2m. Now this is normalized function, so this will become 1. So this is my equal to E. And now in order to solve this one, okay, 0 to L, I am writing this expression as a d upon dx of psi star del psi upon del x, which is equal to, here this expression becomes E. Now in order to solve this further, h cut square 2m. So if I write this one, I need one more term here. So this is what become. If I differentiate this one, this will come del psi upon del x. So I have to subtract this term. So it'll be del. Okay, it should be del psi star upon del x and del psi upon del x. This should be one more term here, and this whole is inside a box dx, and this is equal to E. Now if I differentiate this one, so this will be different this is differentiation. So this will become psi star del psi upon del x, and this is 0 to L. And this I can write is I have solved the integration here, and this is a minus minus plus h cut square upon 2m integration 0 to L. This become mod of del psi upon del mod psi square dx, and this is equal to E. Now let it solve it further. See, if I solve it a little bit more, this quantity should be 0 because psi at L is equal to psi at 0 because it's moving circular path. We already discussed. So this term should be 0. So only now I left with the energy E is equal to h cut square 2m 0 to L d psi upon dx square dx. Now this quantity positive, this quantity also positive. So this whole quantity is positive. So my what I told that for Vx0, potential is 0, the total energy of the system should be positive. So this is coming as a positive. Now we have proved this is positive. Now let us go for wave function. So say now let me write again the Schrodinger equation. So Schrodinger equation says H psi E psi, and E is positive. So this will be minus H cut square 2m del 2 psi upon del x square is equal to E psi. And this can be written as a del 2 psi upon del x square is equal to 2m E minus here 2m E upon H cut square psi. And I'm taking it as a del 2 psi upon del x square. I'm writing it as a minus k square psi, where k is what? K is a positive. K is your k square is equal to 2m E upon h cut square. So my energy will become h cut square k square. E is for free particle energy. Now we know this equation, we know the solution of these equations. What is the solution of this equation? The solution of this equation is psi x should be, say, a type of, say, exponential function. So I'm writing this should be psi x, say, a e power iota kx type of solutions. Now we will normalize and find the a. So this should be the type of solution should be there, and we know the k here, k value here. So let us normalize this wave function. So particle is moving from 0 to L. Particle is moving from 0 to L. So what will happen this one? So if I integrate this one, psi x squared dx, this should be equal to 1. And this gives me 0 to L. This phase will disappear if I take mod square. So I will be having only mod of a square dx is 1, and mod of a square dx will be L, so 1 by L. So my a will be under L root L. So this is my normalization constant. So now my wave function becomes, for this particle, becomes 1 upon root L e power iota kx. This is my wave function. Now we have the wave function. So now let us calculate other physical properties. Now I told that if a particle moving in a circular ring, psi x plus L should be equal to psi x. So from here, what is coming? If I write 1 upon root L e power iota k x plus L, that should be equal to 1 upon root L e power iota kx. This cancels out, and this gives me iota kl should be equal to 1. And 1 means should be minus iota 2 pi. And from here, I can find the value of k 2m pi, say 2n pi. And where n is your, n goes from 0 plus minus 1 plus minus 2 and so on. Cos 2 pi plus iota sine 2 pi n. So 0, 1, 2. So cos will be 1. So this is correct. So now KL. So K will be my 2 and 2 n pi, 2 pi n or 2 n pi by L, where n is goes from plus minus both. So this is my K value, and now I can find my momentum. Momentum, say Pk, or P is h cut k. So my momentum become 2 n pi h cut by L. So what is coming? Is coming like my momentum is cannot be take random values. Momentum when a particle is moving a ring, this wave function, this momentum is quantized. Momentum is quantized. Momentum is quantized. So if I take L is very, very high, if L is very, very high compared to the h cut, say L is in the meter or even centimeters, then the difference between two momentum values will be very small. And you can assume that momentum is continuous, but in reality, it is not continuous. When a particle is moving in a circular ring, a quantum particle, its momentum is quantized. Now, once we know the momentum, P 2n pi h cut upon L, and we know what is L. 2n pi h cut. L is my 2 pi r. This cancels out. So now my P dot r becomes n h cut, and P into r, that is mvr, that is angular momentum. So that is my angular momentum is also quantized. Okay, similarly, we can calculate the energy. We told that energy E is equal to h cut square k square 2m, and now it's h cut square k, we already know. So this become 4n square pi square upon 2m L square. So my energy becomes also 2 h cut square n square pi square m L square when particle is moving in a circular ring. So energy is also quantized. And now let me write the wave function again. So we told that wave function is what? Wave function is psi x of this particle moving in a ring. I told this is the 1 upon root L e power iota kx. And now instead of k, I can write this is the iota p upon h cut x also. And so this is the wave function for a particle having momentum p, psi p or k, psi k. Here you can write psi k, and this becomes psi p now. And similarly, now I can bring this is in terms of n. So if I can also write this wave function as e power iota, and k we already told k is what? K was 2 pi n. 2 pi n by L x. So this is the wave function of a particle when n we already know is 0 plus 1 plus 2. So this is the wave function for a particle moving in a circular ring. And when particle is moving in a circular ring, a quantum particle, we have seen quantization effects that energy, momentum, angular momentum, they all are quantized. So I'll stop here, and next video we'll go more about wave function and Hilbert space. So thank you very much. I'm stopping.